derivative, then we can think about what was the function which gave us that, which if we differentiate gives us that line, and then you would end up with this parabola. But of course, in all these things, you see you also have this additional part here, which is c. This is just a constant that comes out of the integration, so we need additional conditions, like an initial condition for this thing. And all this is nice and great, but why do we need to do this numerically? Well, these are just some examples of functions, really, really simple functions. But of course, we could do stuff like, the cosine. Again, we know the analytical expression for this, which is just a sine. But we want a way to really automate these things all the time. And again, we can get to stuff which is a bit harder to do by hand, I guess, or to visualize, like this differential equation where the actual function is based on the value of the thing itself rather than the derivative of it, and then we get these type of expressions. So all of these things we'll later see how we actually do numerically, but this is just to give you an idea. The most important part to understand is essentially what we're doing is we're saying we know how something changes, and now we want to know what it's about. So if you want to think of this as any type of change, how much rice is grown based on the weather. So we could do the difference in rice production to temperature, or how much the stock market changes based on whatever time or density or whatever is happening there. And if we want to take this back to physics, I guess the most famous and trivial thing that all of us know very, very well is velocity. So a change in position with a change in time is just going to be your, well, we call it speed, but velocity if we want to also take it with a distance. And this is essentially what you see in your dashboard in the car and how you estimate when you will get somewhere. Type of questions that you got even way before high school. A train goes at this speed for this long. Where did it get to, or how long did it take it to get to this city, or things of that nature, which are basically differential equations without calling them differential equations. And if we take this one step further, then what happens if we take the derivative of the velocity? Well, we can just take the derivative of this thing, which is, again, just a second order derivative, and essentially we get our acceleration. And this is where things start to get really interesting, because acceleration is something that we actually measure a lot in physics. If it's gravity, which is an acceleration, or even if we want to think about our car, normally we don't apply a velocity to a car. We don't just start going at a speed. We apply an acceleration, and that acceleration goes into a speed, which goes into a distance. So this relationship is really, really important and is really where physics comes into play. And this leads us to the next part, which is Newton's second law. And this is the basic of everything that we do in computational fluid dynamics, and as I would say also in computational physics, or physics in general. When you're trying to model stuff, it's at the heart of more or less everything we do. But before we get into that, we need to go to the computational side. So we'll change the story a little bit and now think about how do we actually solve these things in a general manner on computers rather than analytically. And we'll start with something really simple. So like we said, we have this derivative. I changed the denominator here to time because we'll try to focus on that just to simplify things a bit. But we want to take any function which changes with time and think, how do we get a general solution for it, for the actual function itself and not its derivative? So it turns out it's not too complicated because we know that the function is based on the slopes. So if instead of looking at time as something which is continuous, we break it up into small bits. So we see t0, t1, t2. We have this difference between them, which we call delta t. And this is something that you hear a lot in anything where they say delta for temperature, delta for time, delta for space. So this just means the difference between these two things. And computers, as we know, are really good at working with discrete bits of data. They don't like having anything continuous. It doesn't make sense to them. So we just take the time and split it up into small bits. And now we say, if we're at this point here, if we take its gradient and we just shoot it straight to the next time, then we will know more or less where we are there. It's not perfect. We have this error here, which is on the same order of delta t squared, actually. And, well, we can now continue doing this. We look at the derivative here and transpose it up to this point and shoot it again and just keep on building like that. We can put this in terms of an algorithmic form, which is called as the Forward-Euler method, and essentially get this type of expression. So this just means that the function at the time of n+1 or after n+1 chunks equals to the function at the previous time plus the change, so the delta t, times actually the function of the derivation. So doing that, we can easily put this into a computer program, do something in, yep, it's this one. Okay, so we can really, really quickly put this into a tiny Python program. And essentially what we need here, we need our time, so the total time that we have, the function itself, the total time that we have, the initial part, so we need to know where it actually starts, and how many steps we have. Pretty trivial stuff. And then just load all these things, and this is the actual algorithm. So we know that the time grows with dt, and the function itself is exactly what we said. So the function of the time of n+1 equals to the time of n plus this difference times the actual function that we got in. So we can try this on something like the cosine. And what we need to set is obviously how many steps we do this. So I set this to be in 2 periods, so 2 periods of sinusoidal. And if we do this, we get this graph. So I'm plotting here actual sine, and we're plotting the approximation of sine, which is the yellow curve. And obviously these are not great. Yeah, it looks pretty bad, I would say. But if we just increase this, so if we change this to, say, 50 steps, and try this again, oh, that looks way, way, way better. And if we now take this up to, I don't know, say 500 steps, well, we're there, kind of there. Or you can just go completely overkill, put like, I don't know, 50,000, and yeah, now you can't distinct them anymore. So the difference is now the errors are so small that it's basically the same function. And this is kind of the tools that we use. And we should say, okay, well, this might be enough, but a lot of the time it actually, whoops, here. Come on, there we go. A lot of the time this actually isn't. So what other ways can we go about doing this? Now all we're doing is essentially taking a point here and projecting it forward. But we could also do the opposite and project these things backwards. So if we look at the point here, we look at the derivative at the next point, and then say, well, let's take this backwards. So we go from this point and use this gradient to shoot up. And then we do the same thing for the next one. So we look at the point here, and then place it back here and shoot up instead. So now we're kind of over-predicting instead of under-predicting for a curve which looks of this type. And it's pretty similar, but it has some advantages, which we'll see a bit later. But it also has some disadvantages. In particular, if we see here, we're now trying to get the function at the point of yn+1, but we need to calculate yn+1, and we don't know that part yet. And this gives us to a nonlinear equation that we need to solve. We normally solve this through an iterative approach, so we kind of just need to do many iterations to do this. And this seems kind of counterintuitive because, well, you need to do a lot more computational time. But as we will see, it has other advantages which actually make up for this problem and can actually save us a lot of time because we can get away with different type of steps. So different type of discretizations for the time. And of course, we still need our initial condition. We can do another method, which actually works, again, a bit different, but instead of saying that we take the gradient at this point or that point, why not take the gradient here at the middle? This should actually give us a much, much, much better approach. But to do this, we need to have the information about what is this point, because we need to feed this into our function, because the function can depend also on y again. So in order to get this one, we need to do a Euler step, so the simple step of shooting forward, in order to approximate this one. So you need to do twice the work, essentially. But what happens is that you actually get to the solution way faster. And we'll see all this kind of stuff in action. So back to our script, and I'll go to this one. Okay, so we have this Euler function that we implemented before. Now we're going to look at the backward Euler. So this is where we went forward. We want to know the solution at the next time, and we use that to approximate what's happening. And essentially, the way that we do that is we use, again, this regular Euler. So this is just what we did before. And we feed this into our fsolve, which is just a nonlinear solver, to try to approximate what the next one is. And then we use that one. So again, won't go too much into the details there, but it's not too complicated except for this part. So fsolve essentially does this for us. A lot of the times these things will not be something as simple as just a standard function, but we will get big linear systems, so matrix systems, and we need to do linear algebra solvers, which can take different forms. And yeah, it can get quite complicated, but we'll see why it's actually important. Then we have our midpoint method here. And this one again, so we just need to do 2 steps. So the first step was doing the Euler part into the half step, and then we need to do the actual using that for another step to get to the endpoint. And okay, so we have 2 functions here. We have the cosine, which we did before, and we'll just see the differences there, and another function which is actually reliant on y, and this is going to be the big difference. So first, let's quickly look at the cosine. So in order to put a general approach here, I've just put Euler with 10,000 points. So we saw earlier, if we put a lot of points, it basically gets to the right solution. So if we try to just run this thing, we're only using 15 points for all the other methods. And if we have a look at the results, well, pretty big differences here. We can see that the Euler method is underperforming, or under the curve. We get our backwards Euler, which is going over the curve, and the midpoint one, even at 15 points, is actually hitting the curve really, really well. And if we increase these points now a bit, so instead of 15, let's take, I don't know, 50, and change this one to 50 as well, and change this one to 50 as well. So if we do something like this, we run it again, starting to look better. The midpoint actually sits so close to the Euler, which is using 10,000 points, which is quite ridiculous, because with 50 points, we get as good a solution as here we get with a lot more points. So let's see how many points we actually need to push here to get anywhere close to a better solution. So let's like push, I don't know, 150 points. Better. 500 points. And okay, this is pretty good, but still not perfect. And we actually need to go to a pretty high amount of points to get anywhere which is as good as the midpoint is at just 50 points. So this shows us the difference between the orders of the approximation. And the more points you use for a single approximation, so because now we're essentially using twice the number of points, and we're doing 2 times the calculations, but we're gaining an error, which instead of being with respect to h, is now with respect to h squared. So the error decreases far quicker when we're using these type of higher order methods. So this is only a second order method compared to a first order method, which is the Euler and backwards Euler. But why did we even want to do this backwards Euler? So if we go back to this other example where we're using 2y, then we can do, just get these guys out, change the initial condition. Where was I? The initial condition is that one. And yeah, just enable this one. Okay, and last one, just for the actual result. And okay, so also let's take these back to a smaller number of steps again. So we'll reset them all back to 15. And let's have a look at what happens here. So let's try this. And what do we get? Ooh, okay, so this looks more interesting. Actually, let's decrease them a tiny bit further. So only take 10 steps in this whole thing. And if we try this now, yeah, now this starts looking really weird. Like, what the hell is going on here? It doesn't look anything like the solution. Well, it turns out that if you're trying to shoot forward, then if you shoot in steps which are too big, the solution isn't actually going to get to the right solution. And if I take this even a tiny bit smaller, particularly the Euler one itself, so if we take this to 9, for instance, and I'll change the mode to 9 just for the sake of it. And we'll try to do something like this. Well, it actually blows up. The whole thing just keeps growing and growing instead of decreasing to 0 like it's supposed to in the real solution. And this is where shooting backwards and doing an iterative position actually helps us a lot. So here the curve, the only one which is actually going towards a solution, is the backwards one. And the reason for that is to do with linear stability and the size of the time step which you can get away with. So if we take this back to, what was it, 15, like we did before, we can see, see where we were. Okay, we were here, and we can actually see that the midpoint one, which was a green one, is actually further away than this one at this type of resolution. So definitely we can see why we might want to use this backwards approach. But if we now increase the number of points significantly, like to 150, well, now the things will change a bit. And the green one, again, reaches where we expect it to. All of them give us a decent result, but the midpoint rule, again, is far more accurate. So this gives us some kind of limits to what we can do. And when we're trying to solve massive, massive systems, sometimes we want to have the biggest time step we can get away with, because each computation takes a long, long time. And the part of doing the nonlinear solver will be smaller than the number of time steps it would have to actually include in order to get away with a simpler method. So saying all of that, let's go back to our slides. And now that we have some idea of the numerical analysis part, well, let's go back to the computational fluid dynamic part and try to make sense of the different things together. So we go back to this force equals to mass time acceleration. And now we'll try to apply this to fluids, because fluids basically just move. But remember that everything we did so far, we just looked at a single point. So we had a point that moves, but a fluid is not a point, it's a field. Anything that moves here, moves there. And similar to gravitational fields or electrical fields, these things work in space as well. So we're not just stuck in time, but now we're in space and in time. So just to give some ideas of what's going on here, the mass we can relate to density through this known relationship. And the acceleration we're going to write as this material derivative. And this is slightly different than a regular derivative, but we'll get into that soon. And so we can also call it a Lagrangian derivative, or a derivative in a Lagrangian framework. And using this derivative and this thing, we can try to have a better look at what's going on there. So we can write it in this kind of way. We're doing this now. These are basically going to be integrated in terms of a volume, a control volume, and this is why we actually replace the mass fully with a density, because you can think of a density being multiplied the mass being multiplied by the volume to give you this density. So this is the form of essentially what we're going to do with the fluids. And what we need to figure out here is what the force is. So what is the force which is applied to fluids? And we get something like this. So the first part is the pressure gradient, and this is pretty sensible. If you have a high pressure somewhere and low pressure somewhere, the force is going to go, or the acceleration is going to go from the high point to the low point. So the difference is going to be in the negative direction. It's going from high to low. And this makes perfect sense if you think of, like, you squeeze something, then it shoots out. You put lots of pressure on it and it will go towards where there isn't pressure. Or when you open your tap, you're creating pressure at where the water comes in, and outside there is just atmospheric pressure, so less pressure. And this is the most fundamental thing in understanding how fluids move. It follows the pressure gradient. We have another part here, which is a dissipative force, which is to do with viscosity. And this essentially is acting in the opposite direction of the force, which is from pressure. So it's going exactly opposite direction. And this is where you get concepts like drag, for instance. And lastly, we have these external forces, which are not from the field itself, but from what's happening outside. So other fields, for instance, gravity or surface tension, or if it's a fluid, which is, for instance, metal, which is in gas form, then magnetic forces, and this is actually called magnetohydrodynamics, and we can do with that stuff like how, with CFD, how galaxies are formed. So this force can basically be anything, but for simplicity, normally just take it as gravity. And again, like I mentioned, we are doing everything in terms of volume, and this is why this density joins this force here. Okay, so importantly, when we looked at the pressure gradient, we need to think what a gradient is. We're now in this three-dimensional space, and pressure doesn't change with time. The pressure actually changes with space. And this operator is called the gradient operator, and it takes this scalar value, this p, which is not a vector, and it needs to know how it changes in all these different directions. So the pressure needs to change in the x, y, and z directions differently. And this now gives us a new set of problems to deal with. Before, we just had to take time and split time into little chunks in that kind of linear way, pretty straightforward. But now we need to take this pressure and discretize this into different directions. And this is where the concept of elements comes in. And why whenever you see stuff in CFD, you normally see it done on a computational grid. The concept of grid is because we need to now take the quantities that we have, the velocity, the pressure, and actually spread them around in space. So here, for instance, this is just like regular squares, and we can just say, okay, so this point is going to be influenced by that one, that one, that one, that one, that one, from all the different directions, and we need to know the differences between all these directions in order to say what is the actual full difference of the pressure. And this also introduced something new. So before we had time, it just goes from one point to the next point. We had what we called an initial condition. Now we need to introduce something which is called a boundary condition. So we need to know what happens at the edges of this thing. We'll show that a tiny bit later. And similarly, we introduced something else which was called the material derivative. And this material derivative, or Lagrangian derivative, again, that gets decomposed into a partial derivative with time and another partial derivative, again, related to space. This is a quite complicated term, a advection term. We won't break that down in because we don't want to do too much multivariable calculus. But essentially, this gives us this form of the Navier-Stokes equations, or at least the momentum conservation part of the Navier-Stokes equations, which we can think of in several ways. So this is this term here. So first of all, this is just the time stepping stuff. So this is what we can solve with a Euler scheme or midpoint scheme or other schemes which are normally more suitable. But what we need to know is what happens on the other side. And this we can break up into a few different parts. So we have our advection term, and this is how the quantities basically spread out, how the velocity spreads out in space. It transports the quantities from one point in the domain to other points in the domain. We have our pressure term that we introduced before, and we just need to divide it by the density because we only want to deal with the quantity related to time here. And then we have our dissipative term, which we can, again, take the density here. So this term, which acts in the opposite direction to the advection and the pressure gradient. And lastly, these external forces from before. So this looks like a pretty complicated equation. It kind of is. There's $1 million prize to show that it's actually possible to solve it with every type of initial and boundary condition. And normally we can't solve this stuff on paper. We need to really simplify it and look at stuff in a 2D approach with saying that something doesn't work here or doesn't work there. So for instance, like a pipe flow we can kind of do as long as everything is smooth, and we need to make lots of assumptions. But in general form, we just can't do this analytically. And the only way to do this is with these type of numerical analysis tools, as we've shown before. And related to this is another equation, which is called the continuity equation or the mass conservation equation. This is the form with compressible fluids. And in here, we have this term, which is this nabla.u, and this is called the velocity divergence. So essentially what we do in CFD is we need to come up with a numerical analysis tool to do this divergence operator and this gradient operator, and these ones are just related to them in other forms as well. So we need a divergence, a gradient, Laplacian, and then we take these terms, these operators, and we discretize them in space. And after we do that, we solve these things on the right-hand side. We then just go and advance this thing in time. That's the whole game that we're playing. And to give some type of idea, this is something that we could, for instance, do analytically. Then we need to have our boundary conditions. So this means pressure in, pressure out, and the pressure in has to be higher. So the velocity will go in this way. And then we say that we have a wall here, which means that there is no pressure gradient crossing this wall, of course, and also that the velocity of the fluid on the wall itself is 0. And just knowing this information, if we simplify it to 2D, we could actually solve this thing analytically. And this is essentially where I want to start part 2 of the talk. So I hope you found this stuff quite interesting, but I think we reached more or less half an hour, maybe a tiny bit more. So I'll just exactly go over what I would like to do in part 2, which is I talked about this material derivative and regular derivative. So I just wanted to explain a little bit what this is, why there is this Eulerian form and Lagrangian form. After that, we'll look at some basic spatial discretizations approaches, so similar to what we did with this time stuff. Look a bit more into this viscosity problem. And after we have these building blocks together, we can actually try to solve together this pipe flow. And if we have the time, maybe we can do this in another talk, or if there's any interest in it, we could look at advanced ways of doing spatial discretizations for things that are not a pipe flow, but really complex real geometries. And I just wanted to finish with showing like a tiny few things that I've been working on the last decade or so. So this is the type of meshes that we actually generate at my current position. So these are like really high order meshes, which you can see we need to fit them to these any kind of shape. And this is something that we did with Rolls-Royce, where we actually created these meshes which are just cut directly into a standard mesh, and we just cut it and we need to do all the geometrical stuff. I particularly like this thing here because this really shows our time and space really, really well. So we can see now how everything is moving with time, but every point here is related to other points. And this is our spatial discretization, or just these particles here. So this was something that we worked on to find new stabilization schemes, dissipation schemes to make sure that this thing doesn't blow up, because it's pretty easy to blow these things up. And lastly, this is probably my favorite thing. This is what I worked on in my PhD for the European Space Agency. We basically use the Navier-Stokes equations and these different numerical models, numerical schemes, to see how fluid would move inside a tank under quite violent motion. We managed to get some really, really nice results for this. Yeah, with that, we can call it an end.
I just want to say that was an excellent talk. It was just an excellent talk. I quite enjoyed the fact that I was picking out little things that I already knew, but then it went on to stuff that I didn't know, and it was all very well explained. Before you leave, I think there were a couple of questions. I think.
Sure.
Yeah, I think Regal had one if he wants to ask it.
Do I need to see them, or will they?
Can you hear me? Oh, yeah. Let me see if I can turn on the camera for added realism. Can you see me?
Yep.
Right. So what I was thinking about it is that when you were playing with those number of iterations there in the cosine approximation, right? So there's something from signal processing that's the Gibbs phenomenon that I'm sure you're aware of, where you have some sort of discontinuity in, say, a square wave, for example.
Yeah.
Yeah. Does that happen as well here when you have not as smooth a curve, or does it just blow up in those cases?
So if we're using these type of methods, we are one of the assumptions that we're making is that the function on the right-hand side is smooth. So it doesn't have these discontinuities. There are ways of dealing with discontinuities, and we definitely do that, not in time because time is continuous, but in space we definitely have discontinuities, and there are lots of methods to deal with that. But again, it was a bit too advanced to get into. I just wanted to kind of explain the real basics. But yes, it is a big problem, especially when you're doing stuff like high Mach number computations, because then you get a shock wave. And a shock wave is essentially a discontinuity in space. And we need special techniques to deal with those type of problems. I hope that answers the question.
Yeah. And the other thing I was trying to understand is whether you, in one of your last slides, was just like the position of a specific, I don't know, differential cube of fluid, or if it encoded more stuff, like the velocity of that thing as well, more.
So I guess that bit I kind of brushed over a tiny bit too much. So we have this, it's called the fundamental assumption of fluid dynamics, where we're looking essentially at a tiny control volume. So we're not looking at the molecular size of things, but we're looking at a particle of fluid, essentially, which is much bigger than the molecule, but much smaller than the domain itself. And these are the kind of control volumes that we describe all these forces acting on. And the important bit where it needs to be bigger than the molecule is because we treat this as something which is continuous. So the whole field needs to be continuous, and this is just a control volume inside that continuous field. So when we discretize it into a computer, on the other hand, we're actually doing this in a discrete sense. And then we are literally thinking about how this is influenced just by its neighbors, in a sense, or within some kind of radius of influence which we can control. And it's not the whole story, but again, like we saw in the discretization of time there, it gets us very close. And the more neighbors we have, the more information we have from other nodes, the closer we are to the real solution.
Is there some sort of rule of thumb to how much you should discretize with respect to the system that you're trying to simulate?
Yes and no. So it's problem specific, very, very problem specific. So if we take something like this pipe flow, we can get away with very, very coarse resolution. If you have a shock wave, you need to have very, very, very fine resolution near the shock wave, for instance. So it depends on the physics and how fast the physics translates. And this is related in some sense to something called a current condition, which is we need the information to not travel faster on our grid than it can. So if you have 2 points, here and here, you need to make sure that it doesn't transfer from here to here in less time than a time step that you're actually moving forward. So either you need to make it smaller or you need to make the time smaller, but one of the two you have to do. But it's basically physics related and physics driven.
Cool. Look forward to part 2. Nice talk.
Cheers. Was there any other questions? Or are we out of time anyway?
I do have one.
Okay.
So a lot of what you're talking seems like it's slowed down by the sort of speed at which you can simulate or do the simulations based on PDE solving or numerical PDE solving for the Navier-Stokes equations, yes?
Mm-hmm.
I was wondering, because I saw something a while ago about actually neural networks turning out to be potentially quite applicable to accelerate PDE solving. And this seems like something where it could apply.
So we are doing that quite a bit, mostly in a different kind of way on the turbulence modeling side. So I didn't touch turbulence really here, but turbulence is the big genie in the bottle in CFD because this happens on very, very multi-scale approaches. And then we need to know stuff that happens on very, very small scales, which affects stuff on bigger scales. And this is very much related to the dissipation of viscosity terms. And this really slows down things massively. And we do use machine learning in those senses to kind of resolve the finer scales and feed it into our simulations, or do stuff like taking big time steps and doing the stuff in between the time steps using machine learning based on just training it on finer models or things of that nature. So yeah, it can definitely be accelerated using machine learning. There's a lot of debate on how accurate it is and how do you quantify the accuracy when you're doing machine learning and all kind of stuff like that. But it's definitely a thriving field and something that's pretty exciting moving forward. So yeah.
All right, cool.
Also, we can do a lot of stuff with hardware acceleration. So we offload a lot of these things to GPUs, which are quite good at some aspects of these types of calculations. And I guess what we're really focused in more, I think, is actually HPCs and how to scale these type of problems to really many cores and making it effective in those kind of scales. So it's fun games to play, that's for sure. Right.
Yes.
Thanks a lot.
Yes, thank you. I think we're all looking quite forward to part 2. This is the point at where we would all clap you off the stage, but I think if we all did that, one thing will either blow up somebody's mic or my computer. So next up we will have the one and only Tecosaur, who you all know from the Discord server. He's currently been working on interactive tutorials within Doom Emacs, and he's going to present more. The stage is yours, Teco.
Thanks. I finally have slides. So...
Mona, did you have a question, or were you doing something else with your hand?
Oh, no, that was me clapping.
All right, cool.
Nice.
Wrong reaction.
All right, let's see. Now, normally I would do this, my slides in Emacs, as it is right. Unfortunately, PDF Tools is currently broken for me. Yay! So let's just stick with the venerable Mu PDF instead. As long as I can select the right window. I've got about 30. So picking is unfortunately non-trivial. Oh, that one.
You're saying you need paper mode.
There you go, yeah. Yeah. I'm still hoping that will actually come to fruition at some point. Okay. So you should all be able to see my screen, yes? I saw a nod. I'm going to take that as a yes and run with it. Okay. So I feel like there's a bit of a caveat that's we mentioned at the start of this, which is I haven't actually done any further work since whenever the last comment was made, like 1 or 2 months ago for the tutorial. Because basically the remaining problems are the sort of less fun ones. We've got through all of the fun sort of little get things set up. So I can do a minimum working sort of demo. And that's the approach I'm taking here, is I'll just give a little sample of how it can look and a bit of the sort of motivation, design, and what it will actually look like as it's currently built to actually write a tutorial. So yeah, hopefully that should be enough to be of interest. So for starters, why are we actually doing this? Well, it's to help people learn some combination of Emacs, Doom, and its modules. And of course, this is something that, sitting around on this Discord, we are all exposed to, whether we like it or not, to varying degrees, particularly if you're one of the brave people who sits in the help channels. And if we're talking about learning Emacs, there's a reputation. And there's some classic pictures, which I'm sure you've all seen, but I'm including for fun anyway. Plus this one, and I think I personally prefer, it's quite nice one, Editor Shapes. I think it's quite a nice one as well. Another take on the difficulty of learning Emacs was, yes, the surface is large. Yeah, and I think we've all felt and now see, or perhaps still do feel even, the ease at which you can sort of feel like there's just too much to get actually, even particularly when you get started, even simple tasks, it feels like it's climbing a mountain. And so, yes, RTFM is great, but for starters, I don't know that many people, when looking at an editor, actually look for the manual as a starting point. And even if you have people that do look for the manual, then there's the problem of actually reading it. And yes, I think with those sort of two hurdles, that cuts out the vast majority of people. So RTFM, as ever, remains a nice idea that is poorly executed in practice. And then, yes, also actually remembering useful bits. I think this is particularly relevant with the Emacs manual because of how massive it is. It does a great job at actually documenting basically everything you'd want to look at. But if you actually want sort of a minimal introduction, that's not so great. So you got sort of at the moment, you got little things, for example, you got the Emacs tutorial, which opens up just one big, I think if I go to, no, I can't, I almost did Emacs here. And then, no, I'm not in Emacs because PDF tools is broken. Yeah, so you've got the tutorial type document, which is just one sort of page of text, which you can go through, which just sort of works, just not very glamorous. You've got the evil tutorial, which just produces a similar page of text for Vim, or evil rather, but interactivity is quite good. So I just did a quick look at the abstracts of just searching for interactivity in learning, and what do you know? People say that it actually helps. Yes, there's all sorts of things about enhancing retention, engagement, and motivation, which are all things which seem like they're rather good if you actually want people to, well, learn, simply put. Now, as is noted in the first source, the challenge is actually implementing it well. Now, this is, and here are a few things if you want to have a look later. Now, here we get on to the actual design of it. Now, when thinking about the design, there's one particular site which actually came to my mind, which is Codecademy, which is where this is what I originally used to transition from the few little things from Python 2 to Python 3, back whenever that was. And so, yes, that worked fairly well for me at the time. So when I'm thinking of interactive tutorial, this is what came to mind. We can sort of deconstruct this a bit, because you've got basically 4 main elements to here. We have an instruction pane. So this gives the necessary background for certain problem/lesson. It gives hints if you want them. Just, yes, all of the about. Then you've got the sort of what I'm calling the user interaction box, which is where you actually do things, and then a little output pane on the side. So that, together with the ability to navigate through the various lessons, to me, I feel like the basic design of Codecademy, and is one that I think works fairly well. So when thinking of the Doom tutorial, I thought, well, we could probably use something similar. So this is the idea that I had, and so I'll split it up in a similar way. So we have this sort of split the window in half, or split the frame in half, and have the user interact with that. And then on the other half, put instructions for what they should do, little navigation bar at the bottom of that, and then some sort of action log. But yes, you can just look at the executed commands and yes, show a history of that and actually make it a bit better. So we can do things like, for example, when a command is executed, like, I don't know, delete line, evil delete line, have it so that you could actually click on it, bring up the help string or help documentation for that. So how has this actually turned out in practice? This is one of the things that actually has been accomplished, sort of, or at least ticked off the main points at this point. And you can see, should be able to see that what we have here pretty well, or pretty closely resembles the design plan that we had. We've got the sort of one big scratch pad on the left, instructions and a command log, which in this case includes the time, the name of the command, and whatever key binding is used to trigger it. I think that's either triggered or just if there is any key binding, it puts it there, which, yeah, actually, I think it does that one, yes. Which is kind of helpful if you trigger something manually, like, hey, there's a key. Okay, now, at this point, I think I might as well jump to a demo. So let's see. If I switch window, let's see. Can I just switch or do I have to stop screen sharing and start again? Let's see. Okay, that stops it, and then I have to start. Oh no, I need to pick an Emacs window now. Which one actually has this loaded? Let's just go for that one and load it if it isn't. Wait a moment. Oh no, they're all called the same thing. Okay, I think. Wait, maybe? No, that's not looking good. What about that one? No, oh wait, no, gives me preview, not that one. Okay. Yeah, this is really fun for you guys, I'm sure. Let's see, not that one. Oh, that looks like it could be it. Okay, let's try this one. So if we go ahead, let's see, is tutorial defined? Nope, it isn't. So in this case, we'll just take a little diversion into my .emacs. And since there are uncommitted changes here, actually tutorial, we can just load some of the code. Actually, I didn't need that. Didn't need that one. Evil tutorial. Yes, let's go with that. And then we can go, and this adds a command, which is its evil tutorial. So we can now go doom tutorial evil. And yeah, this is what you saw earlier. So the idea is that in addition to just telling you what you should do, it actually notices when you have successfully completed something and takes you through it. So what I have implemented here is basically the start of the evil tutorial, just sort of reformulated. So to get through the first step, we need to insert some text, and then exit insert mode. Done. And what's nice here is it automatically goes, you've completed this, here's the next step, which I think is quite handy. So compared to the sort of Codecademy model, there's some nice things which are missing at this point, like hints and sort of subtasks. But I feel like the essential ability to give user information in like a little easy to digest chunks is satisfied here. So yes, in a similar way, we can now look at the moving around. Yes, very nice. And then going to the end, which is, nope, the other one. No. Similarly, yes, we can take us through deletion, and in this case, it just looks at the buffer state and waits till it actually matches specific text. So if I go ahead and actually do the suggested editing here, there we go, lovely. It should, yep, once again, automatically notice. So yeah, I think that's enough to give an idea. Now, you see that we currently at step 4 out of 5. What we can do here is actually exit this with doing tutorial quit. Here we go. Leave the tutorial. And then what's nice is we actually have the progress saved as well. So if you go back to the evil tutorial, we see we're now back on step 4 out of 5. In addition, we have the little sort of navigation ability at the bottom, which, yep, works there. And then I think it's also worth noting that you've got this command block here, which at the moment is showing all these button presses. Oops, I don't do that. But I think that should actually only be active in this buffer. So if I switch the focus over to the instructions, yes, I should be able to do things, and it's selectively just sort of watches what happens in the scratch pad. Now, there are a number of limitations, which I'll go over in a moment, but for now, let's switch back to the slides. So, and there we go, that should be the right one. Yes, there we are. So, that little demo done. Let's just get into a bit of the implementation. So, structurally, we've got this new tutorial module, and it's basically got everything in this autoloads file and a little config file. And what this enables is once this is loaded, it actually checks all of the module files or module folders and just looks for any tutorial.el file in those modules. And simply, if there is one, it will load it, which is, yeah, rather nice. Now, yes, and that's what I just said. So the way this works is when you actually load it, it's going to execute some code which registers tutorials into this, called this Doom tutorial register function, which puts it into an A list. And it says, the structure is quite simple in essence. You have tutorial names and then a certain list which defines what that tutorial is. Then, as you saw, tutorial history can be saved. And the way this is done is via a tutorial progress. Now, what this actually is just an edist file, which when evaluated will set the progress. The history file will just set the progress to what it should be. So it's quite simple. And then when it saves the progress, it just writes out the structure of the progress object to that file. So simple, but it works, which is, yes, one of the sort of nice areas for Lisp in this sort of serialization, deserialization type of use case. So with that little overview out of the way, what does it look like if you actually want to make a tutorial? So the way this works at the moment is there's this define tutorial macro. No, I didn't have the module loaded when I compiled this, otherwise the macro and the doc string would have been highlighted appropriately. Anyway, so one of the things which I think is rather relevant when thinking about tutorials is discoverability. So this is what we have this triggers parameter for. So the idea here is that you can put a list of modes and functions, and the first time that a user triggers one of those modes or functions, I think just whenever they do and it's not sort of, the tutorial is not blacklisted as or completed, one of those two it's a little detail that isn't at the top of my mind at the moment. It will automatically trigger the user, hey, there's a tutorial for this. Would you like to do it? And if the user says yes, it will run the tutorial. Now, what this involves is running the whatever body is defined for the setup parameter, and then you have a whole collection of tutorial pages. You can run through those, and then when quitting the tutorial, it will run the teardown function. So this is, yes, what allows you to set up and the interface and also get rid of anything that you want at the end of this tutorial session. So yes, little version. This uses the same sort of style as use package for plist, which is actually quite easy to turn into a normal plist. For some reason, use package overcomplicates it, but anyway, just to give you an idea, that's what it looks like. Now you have the actual tutorial pages themselves. And the way this is structured is this basically gives the content of the instruction pane and then what to watch for in terms of completion. So yes, the instruction pane, we have titles for each tutorial page. We have the instructions, and what this is at the moment is just the body of the instructions, so sort of the org as a string. Now, we can also do is, and you saw this happen in the Evil tutorial, you can initialize the scratchpad to some certain content. So that's what the template parameter gives. Then when starting that page, you can also run any setup code. And lastly, to allow for automatic completion of a certain step, you can supply a test parameter. If this is omitted, it just means you need to go to the next step manually. That's all. But yes, this is down to the sort of automatic paging. Okay, so what's next with tutorials? For one thing, I think subtasks are quite a nice idea. So for example, if you had like, I don't know, use H, J, K, and L to move around, you could have like a checkbox for each of those. Or particularly have, maybe that's not the best example, but for example, a multi-step task. So I say, okay, you've now looked at all of these things. So let's all cap this off. We'd like you to do this, 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 and that. And you can have checkboxes for this, 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 and that, which get checked off as those individual tasks achieved. I think that'd be quite a nice way. One of the ways that this occurred to me is that it's actually done by basically just generating more pages, but that doesn't allow for things to be completed out of order. So yes, this complicates things, but I think deserves a bit more thought. Now, lastly, I think it'd be rather neat to actually have all tutorials written within all document. This is still a work in progress. The idea at this point is that we'll work out what's going on with the defined tutorial macro for starters, and then once that's all sorted out, actually end up writing away, probably using org element to transfer an org document to a defined tutorial macro call. All right, so that's all I've got for slides. At this point, what I'm inclined to do is actually show you what the sampled Evil tutorial looked like in terms of the definition code. And if you've got any questions, this is a great time for them. So yeah, this is the tutorial.
I thought you had some sort of a checking for when you did that move down and move whatever it was in that first demo there. You say you can't check for multiple things?
So the way that works is just check when the cursor's at the end. So the actual text says just move around, have fun, and then move point to the end of the buffer to go to the next stage. That's how that particular task operated.
And you do that by running some sort of timer function, or is it looking at the
I'll
command history?
switch to Emacs again so I can actually show the code. So wait, which window? Oh no, I've got two windows showing the same thing. Let's see if I hide function. Okay, yeah, that's this one. So, and let's just move that one out of the way so I don't get confused. So this is what it actually looks like for the definition of the Evil tutorial. So let's see. Move the cursor task you talk about is here. Then you see how this operates. You've got the instructions content just put in here as a string, and then you've got a template, and you can see here's what the test function looks like. So so the test functions just take the form of an Eliterate expression, and what happens is it's evaluated on a timer in the Scratch buffer, and it's simply taken that any nil value means it's not done. As soon as it returns a non-nil value, you go, hey, this indicates that the person doing this tutorial has successfully completed this task. So yeah, and so you can see similar examples. If I just go, for example, what does the test look like? Yeah, so in this case, looking at the editing, we just check that it matches the expected content. Now, if we're looking at executing particular commands, we've actually got a help function here, which is command log starts with. I don't know if we've actually got a command log in this instance of Emacs. This is a different one I accidentally selected. Let's see, tutorial. I might log. Yes, so you can see what we actually have here is a log of all of the commands executed from the buffer. So you can check things, for example, is the last command an evil delete? Yeah.
Cool. There is something for run hooks, which you give it several functions, and whichever one returns true, I think it signals that the thing ran successfully. So you could have something similar here where you have actually a list of test functions, and eventually they all return true. And then you do that as like the check for multiple tasks.
I mean, the way I'm currently thinking,
you have to have some sort of state somewhere else.
Yeah, what I'm currently thinking is that if you had sort of subtasks, the way that might be done is via you have this page, and then you probably have some separate sort of structure, like, let's see, subtasks, and that could be some list of, I don't know, description, and then some sort of test function, something like that. And then what happened is you have a number of these, and then this would used to be actually generate some sort of subtask section which is put into the instruction content. And then yes, this would sort of supplant, supplant the test function or test parameter, and then you're evaluating all of these, checking to see which ones are true, using, and then probably have some like last result variable, and if it changes, then update the content in the instructions buffer, and when they're all returned true, then move on to the next task. There's a sort of form I'd imagine this taking. But yes, this is still on the to-do list.
I had kind of comment / question.
Sure.
So it seems like you designed this intentionally to be modular, being able to add tutorials, and I think that's really exciting because sort of I could see a step beyond a tutorial where people were able to design challenges in a sense where you can have your basic tutorial, but then it's like, oh, here's your Doom challenge, and you can get creative on like, here's something, try and do this task and in new and creative ways. I don't know, I think this is excellent, and I would have used it as a new user.
Well, that's good to hear. Because yes, I think like one of the things for actually writing tutorials, which I anticipate being difficult, is actually being able to accurately pick which are the sort of difficult things that deserve a task or a mention. Because it's all the things like once you've learned things, you forget the difficulty in learning them and where the sort of problem points were. So what I'm hoping is once this is actually all in a state that we're happy with, my plan is basically to ambush some of those users sort of know how you occasionally get sort of new enthusiastic users on Discord, and just basically ask them to like write down or give us details on what they find difficult and try to add those points to the tutorial, sort of check them off. So yes, something like to actually make sure that once we've got a framework that's good, to actually make sure that the particular sort of lessons that we have are the most useful ones. I think it's going to be, well, not easy, but not too hard either. Just, yes, definitely going to require some thought. No, yeah, I mean, yes, regarding it being a bit general, I mean, that's nice to hear. And I'm really glad you brought that up because, yes, it's called the sort of Doom tutorial, but I guess if one were to be a bit more accurate, you could call it the, what, sort of interactive task completion framework or something like that.
Yeah, that's actually kind of what I wanted to ask. So I definitely see how this is perfect inside Doom Emacs or Emacs in general. But it would be really, really useful to do other stuff like tutorials on university projects or stuff like that to give to students. But it only lives inside eLisp, so that's the only limitation I can really find here. But it's really seems really, really cool. I think, for instance, some stuff to do with writing some eLisps function and actually teaching eLisps this way could be really, really powerful.
That actually is something which has occurred to me as an eLisp tutorial. I think that'd be really neat because you could basically go through, I think, for example, with somebody's configuration, particularly if you don't know any Lisp, and you just suddenly see all this eLisp, you go, what is this? I don't like how this looks. Help. And so something which just sort of takes somebody through like the basics of eLisp, I think can work really well here. Because you could have things like turn the scratch buffer into an eLisp buffer and tell them, for example, tell the user, okay, here's some content. Just like give them like some basic expression like set Q A1 and say this is going to set A to 1 to evaluate it, and then based on whether they're using evil or actually using just standard vanilla, work out what the key binding is to actually eval the expression and just tell them, do it. And then from there, you say, okay, now you try writing something and sort of evaluate it. And you can set the sort of test function, just watch the variable values. And so you could even have that be more advanced, like define a function called this that does these things. And I think you could go up to that point of sort of interactive stepping through the basics.
Yeah, that's exactly what I had in mind. So yeah, sounds good for that.
Because I think like when you get to that sort of thing, particularly, like just in terms of the experience, I think that's going to beat out anything you can possibly have as some sort of long document. If nothing else, because even if you have exactly the same content as a long document, I think there's a lot for being said for tricking people into doing more than they thought they were signing up for, basically. So by having it as sort of this 1 page at a time, one step sort of format, I think that compared to some sort of, I don't know, 20-page full sort of eLisp intro document, I think it's got a lot better chance of people actually giving that a shot. Anyway, so yes, mostly there. I'm keen to see where this goes, but yeah, poking me or having a look at the code and how it works would definitely be appreciated to actually sort of get this over the finish line. So,
Lesser. Oh, sorry, did I interrupt someone?
Well, I was just going to ask, what's the barrier to push this? What's your barrier to completing this or putting it into
okay.
you know? Yeah.
So there are a few things in terms of just like using Emacs, which I think would be like as a tutorial, which we'd want to support, which currently don't work. So for example, if I were to just go back to the evil tutorial, we have this scratchpad here. And if I change, for example, the major mode, definitely something else demo to people, it instantly stops working as the scratchpad. You see, I'm doing things here, it's not appearing in the command log. And so having sort of minor mode type things persist past the major mode change barrier is a problem which I have had a bit of a look at so far, but so far, yes, no luck. And I get a few things which look like they might work, but yeah, it's a bit funky. Trying to get things to persist past sort of buffer local things to persist past changing the local mode. Something which I think could work perhaps is when you just have one buffer, just saying like because of course this buffer exists within the window, to sort of check that assign this window to a variable, check that the buffer within the window has this minor mode set up, and if it doesn't, do it. But then there are other things this one would quite reasonable to do. For example, like tell people, okay, this is how you split a window, and like, okay, that's great, but now you're sort of changing the window configuration, and that sort of breaks that. So yeah, I think it's probably would best be treated not as a sort of hard, don't do anything until this is solved, but sort of in a longer term view is definitely something, or sort of a mode of interaction I'd like to enable for that sort of more sort of thorough introduction to Emacs type tutorials. But yeah, I think there's a lot of things you can do without that being supported. So yeah, not a hard blocker. Yeah, and I think there also might just be one or two lingering bugs, but I forget exactly what's going on.
Well, unless there are any more questions, I would like to thank Tecosaur for a great presentation and for all of his work on the Doom tutorials. I think now we're going to take a quick, about 10-minute break so that people can grab water or go use the loo or summon station or whatever they do. So we shall meet back here in about 10 minutes. And after that, Yamarko will be presenting auto-activating snippets.
Can I postpone my talk again? I'm really sorry, but I'm sort of heat stroked. It's really hot outside, and I can't be as hyperactive as I want to.
That's fine. In that case, we'll meet back in 10 minutes with Constraint Programming by Lejon when he joins back.
Oh, that's cool. Yeah.
Yeah. Okay. In
I
that
have
case,
to say,
I read the blog.
the upside of like cramming way too many talks is even after the inevitable, last minute cancellations, myself included, we still have like a bunch of talks for the the conference. Yeah. So
Just means I just
you
need more
know
time.
how
now.
airlines overbook? We're basically doing that.
yeah. Okay. Then we shall meet back here in 10 minutes. That is 5:25 my time. That'll be probably closer to 5:30, but whatever increment of 10 minutes is your local time zone.
Cool. Oh, one little thing I'd just like to add is just my congratulations to Elkin for getting the taco as it was intended.
No, very good. Sorry.
That's just like Easter egg from the presentation.
Yeah.
So, yes.
No.
I always keep an eye out for tacos.
Okay. Cool. I'll see you in 10 minutes.
Wait, Teco, are you here?
I am.
Yeah, I feel like I lost concentration or something, but like, what are the main kind of boring things left to do with the tutorial module before it's like ready for merger and Doom?
You must be asking this question about 2 months ago when I was actively working on it.
That basically means there's no bugs and it's ready now.
Yeah, obviously.
It's not far off, I don't think. Like, we can, like, as seen with the Evil tutorial, it does mostly work, at the very least, for basic things. So I think, yeah, the list of things that can be done is probably quite decent. This sort of design structure is probably, I mean, that's probably fine too.
I will say that I feel like the Doom tutorial thing. I mean, is there any other than it's fun to put cool stuff in Doom? Is there any reason why it can't be like a standalone like tutorial package?
What do you mean by a standard? Do you mean like outside of Doom?
Yeah, because having like an interactive Evil tutorial is useful outside Doom too.
Yeah, this has occurred to me, and I think that's why I've actually gone to a little bit of effort to have it so that the entire code is currently I think it currently has no dependencies.
Hmm.
Like no editable Doom dependencies at all, I think, at the moment.
Mm.
Oh, no, it does have a little one, which is to do with the workspace. Okay, other than the workspace stuff, has no sort of Doom dependencies, and so that could be. So what this could actually happen with this is this could be published, I don't know, maybe under the Doom Emacs org, why not, as a Doom tutorial package, which is then used by the Doom tutorial, instead of having this giant tutorial.el autoload. When I say giant, it's not that bad, it's only 400 lines. But yes.
Yeah, well, I mean, that makes sense. I mean, I do like the idea of like having tutorial.ls like things in modules, because generally like modules are probably going to have like module specific stuff, but things like the basic evil mode tutorial could probably be externalized. So you can probably just have both, and have all upside, no downside. Oh, god damn it.
Yeah, I mean, I think it does make, to me, it makes sense to have sort of the tutorials just shoved in the folder for particular modules. But yes, I mean, look, I'm not entirely sure how you would use this, because like standalone, because would you have packages that ship their own tutorial.el, just sort of in the hope that this package might be installed?
Probably not, but you probably wouldn't be able to get like the automatic stuff that Doom would eventually do with the modules, but you could probably have like a tutorial repository or something for packages.
Yeah, I guess people could write particular tutorials and publish them as packages. Yeah, no, that could work. Yeah, so there could probably be a few bits, like this currently is written for Doom, so yes, there is the workspace stuff, and yes, there is also this autoloaded function here called Doom tutorial load modules, which looks at the module paths. But yeah, these are sort of things which could be sort of, yes, separated out from the package overall, and all wrapped with a does Doom exist type bit of code. So yes, and then published separately as a package under the Doom Emacs org. Yeah, I think something like that could make sense. Says, yeah, if anybody wants to try writing tutorials, actually that would also be something quite good, because I think something which would be quite helpful in working out what's left to be done is simply seeing what issues crop up if you actually try to take it and run.
Yeah, good point.
So if anybody has modules they feel like they can write a tutorial about, then yeah, I think yes, this branch is. If it's not up to date with Doom's Master, poke me and it will be. So yeah, that should make it somewhat easy to try out.
I don't think I've rebased it in a while, so it probably is quite outdated.
No, it is up to date because I rebased it about half an hour ago.
Oh, okay, fair.
Yeah. Unless Henrik has sneakily been pushing comments during the DoomConf.
Okay.
Henrik, is your mic not working or something? Just seeing the comments in the DoomConf, not the Oh well. Yeah, Henrik, I'm still looking forward to when you do your like State of Doom presentation. I remember the talk about that last year, like, yes, the internet is not good. So yeah, I don't know, just mentioning that.
I realized I just recorded all of that conversation without necessarily meaning to. Okay, let's stop this part and I'll upload this. Well, I won't upload it, I'll test it out.
Yeah, Yeet, if you give me the first part of the first talk, like first, I don't know, 20 minutes, that's probably good because I've got everything past that.
Okay.
with
I
like
probably,
Discord as well?
I don't have the first 20 minutes. I probably have the first 10. No, the sort of the latter 10 off of that sort of that section. I'll send you my clip. It's quite large. I might need to cut it down, but yeah.
Yeah. Deleting and reinstalling all my drivers got me in somewhere when he was going over the org going through the org document and showing like that graph in it.
Okay, I think I have those. I'll check. I think I started recording around near the end of where he was talking about where he came from, where QYU came from. Oh, that's a chunk file. Let's have a look.
I don't
Okay.
think we missed too terribly much of actual.
Yeah, I got to the basic differential equations.
Oh, lovely.
Okay, so I will send that over to you. That is 1.5 gigabytes. I'll figure out a way to send that to you, and then you can stitch it together.
Yeah.
Time to make another burner Gmail account.
Get a USB stick and just stick it to a pigeon. Fly it up here.
To be honest, mailing you a USB stick would probably be one of the easier ways to do it. No,
Just send the frames as email attachments.
Yes.
Is
Vigor
excellent.
here?
Sorry?
Pass it to me.
Is Vigor here? Yes. But he may not be paying attention. Oh. I just read his comment that we should write a tutorial that teaches people how to write tutorials. And I just wanted to let you know that I'm actually way ahead of him there because there is a tutorial file in the tutorial module about writing tutorials.
Excellent.
But is there a tutorial for writing tutorials?
I mean, in a way, that is what I just described.
How combinatory is the tutorials planning to get with like stuff like email and the several different email you can use, and then like having org attached to it, or HTML. I forget what the email ME4E flags are.
Actually, that raises a good point, which it would make probably a fair bit of sense to allow tutorials to also have like a when parameter to check the conditions in which the tutorial makes sense to be available.
Yeah, because like org snakes into a lot of places.
Yeah, like that is the sort of thing that yes, it is flag that could be. I mean, you could already just like wrap this tutorial declaration with a when. I mean, it's not. You can't do it now. It's just not built into it. But what might make, yeah, maybe an after would make sense. Yeah. There's a good idea there. Definitely needs a little bit more thought.
Should just try to take one of the simpler configs and like take the full config as a tutorial or teach part of it or something.
Yeah, just use TK's config as a tutorial.
Yeah, I was going to suggest that, and then I said, yeah, maybe a simpler one would be a better place to start.
Yes, take the 5-hour guided tour of my config.
Only 5 hours, wow.
Turn into an audiobook.
When did somebody do like the calculation for like based on the word count and the reading speed, how long it would take? I think it was less than a day.
I think at some point you were discussing doing like a narrative reading of your config.
Oh, we did discuss it. dramatic reading from the
Yeah.
config.
That would be pretty good.
This has to happen at some point.
That has
Are you going to be?
Can we get James L. Jones to do it?
Actually, one of the great things about doing that from Emacs is that by nature of my config, we automatically get a dramatic pause at the start of the reading, or I wait for it to load.
If we really
So
want
are we
to,
starting Snap
we could.
soon? I mixed Swedish and English.
We could hook Teco up to a recording.
Hello?
booth
Can you
and
hear me?
use, text to speech.
Can anybody hear me?
Yes.
Wait, I think Lejon
No,
is
we
talking.
can't hear you.
Yes, we can hear you.
I'm getting mixed messages.
I can hear you.
I can hear you.
We can't hear you.
I can't hear you, John.
They're all lying to you. We have no idea what you're saying.
Who's talking?
All right.
This is Doom.
What is speech?
Gaslight. I'm not sure if you can actually hear the clock tower bells, but yeah, no, with that, it is 5:30. Put it in chat that we're starting, but Lejon, however, Lejon, if you want us to begin with your excellently written talk.
So my master plan of changing my name and making people pronounce it has been working. I see. I'll start sharing my screen. Hello. There. I trust you can see this now. And here's my almost Flugo-like presentation stuff. So I'm going to be talking about constraint programming and like how the basic principles of it work, and I've already written about it on my site that refuses to load. So I'll be moving a bit quicker than that text. So if somebody like doesn't understand what I'm saying, it's probably my fault, and please interrupt me because I can't see anything when I'm writing. So yeah. Let's see. So we can first start with like why are we doing constraint programming? What is the purpose? So it kind of all boils down to P versus NP, which are like the easy problems and the hard problems. Easy problems are kind of uninteresting, so they are stuff that can be done in polynomial time, and hard problems are problems that require search. You have to like try different solutions and see if they work, and then if they don't, you have to backtrack. And like yeah, what the formal definition is it's non-deterministically polynomial, which means that if somebody gives me a candidate solution, like a bunch of values that they think might maybe is a solution, I can check that in polynomial time. So it's essentially easy to check, but we don't know if it's easy or hard to solve that. And then yeah, constraint programming then is a technique to solve these hard problems fairly quickly, and then also make it easy to formulate new hard problems and solve them also quickly. We have like a general framework for solving hard problems. So I'll be going through this with an example problem called n-queens. N-queens isn't quite NP hard, but if you, yeah, I'll just start with describing what n-queens is. You have an n by n chessboard and n queens, and you have to place them somehow so that they aren't attacking each other. So this third queen here is illegal because it attacks the second queen. And the problem is to place them out so that they aren't attacking each other. It isn't NP hard by itself, but if you start out with some number of predefined queens, it suddenly becomes NP hard. Sort of like how Sudoku becomes hard when you have, or becomes easy when you have a blank board. You can just fill in everything. But I'll be going through with an empty board. So before I said that hard problems require search, some form of brute force search. And so let's start with just doing that. We will go through each possible configuration of queens on this board and see, when we place out one configuration, we'll see if it's legal or not, if it's a solution or not. So like we just start by placing out some queens here. It isn't quite efficient. We see here that these are obviously attacking each other. So we'll undo our last move to try to see try another combination. So we'll place it, in the next available spot. And this is still also attacking each other. And we can just continue going through it like this. We will always have bad solutions because these queens are still attacking each other. But we're still going through all the combinations, so it's what we want to do, sort of. And then now that we've gone through all the combinations where these three are up here, we have to undo two times, because we don't have any more spaces to put this last queen. So do 2 undos, and then put the third queen in its next position, and then we can continue going through it like this. But it's obviously very inefficient. We don't want to do it like this. It's kind of stupid because these are still attacking each other. So what we want to do then when we place our first queen here, we don't want to place any more on this row, because they are essentially by default bad. So what we'll do instead is that we'll place, once we've placed one queen, we won't place any more on the same row. We can model this sort of with variables where we have integer variables like this. Let's see. These are queues, by the way. Where each queen can move freely along this x-axis. Hello? So when we first decide where queen 0 will be, somewhere on this x-axis. And when we do that, we will just place our second queen on the second row somewhere. We are getting in the way now. So first we'll do the same thing again. We'll place the first queen in the first place where it can be, and the second queen at the first place, and so on. And these are obviously, for the same reason as above, illegal. We don't want to place them on the same column. So in order to keep track of this, we'll use something that mathematicians usually call a domain, a set of variables, a set of values that are valid for each variable. So for queen 0, each of the valid variables are these things above here. I wanted the blue color. These are the valid variables for values for Q0, 0, 1, 2, 3. And the same thing for this queen and this queen and this queen. So first we'll place one queen in the first position here. And then now we'll strike out all, the definition of putting out a queen now is to remove all the other possible values. So all of these aren't available anymore, because a variable can only have one value. So when we fix one queen to a variable, it means we've placed that on the board. And then we can also remove the values from the other queens. So for example, the first queen can't be on this row or column, and so on, because they are attacking the columns. And the same for the diagonals. So now we have removed all of the values that are impossible for the other queens as well. And it's time to continue our search. Now we can't place on any of the red squares, so we'll place the queen 1 on the first available square, which is here. And then once again, we'll remove all the other squares on the same row, because that's what it means to be placing a queen. And then we'll remove all the other squares that are illegal from these squares. And this is kind of also an important thing, because as you can see here, Q2, the third queen, can't place. They don't have any squares that are legal anymore. By definition, this problem can't be solved at this state. because we can't place the second queen. So once again, we have to backtrack. We can backtrack a bit early because we don't have to place the last queen. We already know that this problem is illegal. So then I'll use my handy Control Z button and continue undoing until we remove the queen that it placed during search. So now we have already placed it on this square, so we can't do that anymore. It's an illegal move. And we now have only one solution left, or place left to place it. And once again, we can filter out all the illegal positions. And now another interesting thing has occurred, because this queen right here has only one place left to be. And as we said before, placing one queen is the same as reducing the domain of that queen to size 1. And that is what we have done here. So we automatically placed one queen in this position. And because we've placed one queen, we can also remove all the illegal domains again. We can filter out all the illegal values. And then we're also, once again, forced to backtrack because this last row has been blacked out, reddened out. And now we have to backtrack again. And what we do then is we backtrack to the last, we undo the last queen we placed manually and not automatically. So it would be this one. It wouldn't make sense to undo this move because it's only one possible move, right? So now that we have removed the queen 1 here, we don't have any more places to place queen 1, which means we have to backtrack further. We have exhausted this part of the search tree. So now that we have already exhausted this position here, so we'll move on to the next one, which is this queen. Oh, please interrupt me if I'm moving too fast, by the way. I can't see much. I don't even know if you guys hear me or not anymore. But once again, we'll remove all these illegal values. Let's see. And here's also an interesting thing. We have once again, automatically placed a queen here because we once again have a domain of size 1, and then we can trigger filtering again. So now we filter out these values, which in turn also, so automatically placing this queen here reduced this queen's domain to 1. So we place that also automatically, which removes this value as a possible value, which automatically places the queen over here. So now we have a final solution. We have repeated this process until we have placed all the queens. We have reduced all the domains to size 1, which means we have a solution. And as you can see, no queen is attacking each other. They're all away from their diagonals and rows and columns. And this is kind of what it means to do constraint programming. What we do is we have a set of domains that stand for a set of legal values, and we have some constraints. And then, in order to fulfill those constraints, we do some search. We just guess values for these variables, and see if we can remove illegal values from other variables, which in turn can cascade. This can create a cascading effect, as you saw here in the last example, where fixing one variable leads to other variables also getting fixed, which once again triggers more and more inference, essentially. And that is kind of the part that is intelligent. The brute force part is kind of stupid in some sense. So now I've basically exhausted what I was talking about in the text tutorial. So if there's anything here that was kind of unclear, now would be a good time to ask, because from now on I'll use this as a starting off point to talk about other stuff. No questions? I'll continue.
No, I just wanted to clarify that we can hear you quite well. Yeah, I know you did say that, but I didn't want to interrupt you.
Yeah, sure.
If there are any questions, then people will ask it in the Discord server, and then I can relay that. Somebody can.
All right.
Yeah.
Good. So,
quick question.
Yeah.
So this is still brute forcey in a way, right? You're still going through several, but at every point you do have sort of a division there on the search space. So I wonder if there is some kind of metric for how fast can you cut on the search space on each decision you make. And it's easy to see, for example, to count how many for every queen position, how many other places that you're throwing away. But then at some point you need to go back and erase the constraints that you have. So it's not as simple as just counting and dividing by that number. So what's the way to approach this sort of benchmark predicting?
Yeah, you have to like measure experimentally, basically, because it can be kind of, there are so many moving parts in a high-end constraint solver. You have a bunch of different constraints. There are a bunch of variables, and like it's kind of chaotic, honestly. So you have to like benchmark using real problems, and yeah, kind of very simple decisions on the human part can also affect performance quite a lot. And it's kind of something I will talk about later also. But yeah, basically I have to measure time. I don't think there are some solvers that are kind of more. There is a thing where you create constraint propagators that are kind of stupid but very fast. So they remove all the easy targets. So, and there are others that are very intelligent, but they're also very slow. And choosing which one can be kind of hard. And you have to like test which ones are faster. So moving back to the presentation though. Constraint programming is kind of made up of 3 different parts. One is modeling, which is kind of formulating the problem. What we did before was we formulated the problem as 4 integer variables here that stand for a coordinate in this square. And then we formulate constraints, what values should be illegal or not. So like doing that part, formulating the problem to the solver is called modeling. And the inference is doing this intelligent stuff with the cascading effects where you remove illegal values. And search is sort of the last part that ties everything together, where you're doing the brute force search and guessing, basically. So I'll talk a bit about all of them, I think. So search, there's a bunch of decisions to do when we're doing search. The method we used in the example here, where we just took the first available value, isn't necessarily always the best approach, because which decision you make there can affect performance quite a lot. So as an example here, we will say we are somewhere in the search tree, and we know that we like, as omniscient creatures, we know that branching on X will definitely lead to forcing us to backtrack, because some constraints there will trigger and it will empty some variables domain. But the solver doesn't know that. So the thing that could happen is if we search on all the other variables first that are kind of, they don't trigger any backtracking, we'll get a sort of a search tree that looks like this. So we fix here no, and then at the bottom here we branch on the X value. So X is set to some value, and that triggers a backtrack, and then it has set to another value here, whatever, which will also trigger backtrack. And this thing will keep repeating throughout the search tree. So we'll have quite a big search tree here. And all of this work that we're doing above with respect to when we're branching on the y, z, and u values variables, we kind of got wasted because we're doing all that work, and then at the end we realize that was bad. So what we want to do is we want to choose the variable that is most likely to fail first, hence the first fail principle. So what it would look like then is that we're coming into this part of the search tree, and we decide to branch on the x value, and something happens which triggers a backtrack, and then we go back and take the other value, and we backtrack, and then we're out of this part of the search tree where branching on x will lead to failure, and then you can almost immediately go back and do the other part of the search tree. So as you can see, like this part here, it could be huge. It could be hundreds of variables, which would be insanely inefficient. So what you want to do is you really want to know early on which parts of the search tree are bad, are illegal. So one very simple way to do that, which is kind of very intuitive, I guess, is that you just choose the variables that have the smallest domain. So say that if x had a domain of just 2, that would probably trigger a lot of cascading effects that could possibly lead to failure. Whereas if you had another variable that has hundreds of values, that would make it much less likely to trigger a backtracking. So you could search on that later, where it's much safer. There are, of course, a bunch of different ways to do search. One of the kind of interesting ones is called conflict ordering search. Or I mean, all of them are quite interesting, but I'll choose this one in particular. So say we have a bunch of variables here, x1, x2, x3, x4. They all have a domain of size 3, and they all different constraints. So each of these variables have to have different values. But because they only have three legal values each, it will inevitably lead to one of the variables having no values left. So this model here would lead to failure. We have to backtrack. But those variables aren't the only ones. We have a bunch of variables over here also. Let's say I have domain of size 2. But they don't have any constraints, so they can't possibly cause any backtracking. And I'll show you what will happen if we choose these variables first. If you choose these variables first, we'd kind of get a search tree that looks like this, where we just branch and branch and branch without doing any inference because they don't have any constraints on them. We'll get a very deep search tree, and then at the bottom here, we get the search tree that prunes these variables, and they obviously will lead to backtracking because that's kind of the nature of these constraints. And then we have to go back and backtrack, take the other possible route for the fourth variable, which we'll get an identical search tree. And then we backtrack and choose the other value for the third variable here. And then we choose to branch on variable 4 again, which will leave us with more of these search trees. And as you can see, this will get huge. It will be humongous, and it's all wasted because we are just repeating the same work over and over again because these variables aren't doing anything. They aren't triggering any search. So what conflict ordering search does is that it keeps track of which variables were causing a backtrack last, or in which order that happened. So if we're branching on variable x1 here, and that would immediately trigger a backtrack. That would be kept in some sort of ordered structure or something. And then next time we're choosing a variable, we'll choose x1 because that was the one that failed last. So, and that could mean that it has a higher chance of failing again. So, according to the first fail principle, that would be a very smart decision. And then the search tree would kind of look first similar at first, because we still have some other heuristic that chooses these values. Complete ordering doesn't really make sense when we haven't had any failures yet. So we get the same shape here, and we backtrack and do this useless work again. But this time we won't branch on one of these useless variables. We will use one of these variables over here, which will trigger a backtrack again. So we'll have a shape that looks something like this, which is a lot smaller than this one. We'll have, I'm not sure if it's exponential, but it's going to be huge compared to this one. So complete ordering search can be very, very, very nice, essentially. Especially when you have, like, you know, variables that are kind of independent and you don't really want to branch on them first. And then there are a bunch of different ones that are using all sorts of different metrics. But I think Teco showed me a Julia solver that was a constraint programming solver that used some machine learning, because this process here, there's kind of a research initiative to make search. Normally, like previously, you had to choose which search algorithm you'd wanted to use in a constraint solver. But there has been a movement to do, like, to make it a black box, to make it good enough for most users, where you have used some form of machine learning, for example, to just choose the right algorithm for this specific problem, which will make it much easier to use, and you can just focus more on the model input, which is kind of the thing that is unescapable. You have to formulate the problem somehow. Doing search is kind of it would be very nice to have that as a black box. Let's see. Next, I wanted to talk about sort of the intelligence part here, or the inference. I want to talk about a possible data structure for the domain. So there are a bunch of different ways to make a domain data structure, or there are a bunch of data structures that I can use for the domain. One of them is kind of like a bit vector, I think, that's very space efficient. But I want to talk about a data structure that is called sparse set. So sparse set is kind of cool because they use this property of constraint programming, that these sets are, you never add anything to the sets. You're always only removing stuff. You can't add more boards to the search board. It doesn't make sense. You only remove available or legal values, and then you want to add them back again during backtracking. So you could do some copying stuff, but there's kind of an interesting way to do this. So this first array, these are two normal arrays, and in the first one we populate it with values. So say we have a domain from 0 to 4. The second array we populate with pointers pointing towards these values. So give me a minute. And then we have some indices that annotate like which value we want. So how to use this data structure is, say you want to see if we want to access element number 4. Then we use this lower array and go to the fourth element and go see where that points to, and see that is the value you'd get. It kind of looks kind of confusing right now, but we'll see what happens when we start removing stuff. So in this sparse set data structure, we can have an operation that removes elements. And what we do then is, say we want to remove element number 1. What we do then is we swap this value with the last value that is in the sparse set. So what would happen then is we have 4 here. My pen is disintegrating. And then we put the 2 over here. And we adjust the pointers also. So the pointer goes to the correct boxes. And then we have a sort of size indicator that says how big is this sparse set. Everything to the left of this arrow here is part of the set, and everything that is to the right isn't. Those are the elements that we have removed. We can remove more stuff from this. So let's say that we want to remove element number 0. We do this same procedure again, where we swap these values. We swap the value that is immediately above the threshold. So element number 3 goes over here, and 0 goes over here. And we move the size indicator. And as you can see here, it's kind of magic. These parts here that aren't part of the set, these are ordered according to how recently they were removed. We removed 2 first, and we removed 0 second. And if we do this once again, we'll see that the removed element will be put at the head of this kind of queue. So if you remove 4 here, it will be placed. Too many arrows. It will once again be placed. It will be placed at the leftmost position in the. Dang it! This is kind of hard now. Two. And now, yeah, 4 is part of the most recent removed item. So now, if we want to remove or undo, we want to backtrack. We want to add back the values that we have already removed, but we don't want to remove all of them or add back all of them. We want to add back only those that were removed since the last time we made a such decision, the last time we made a guess. And the only thing we need to do then is say what this is the point where we last made a guess, right? So we want to do these removals. The only thing we need to do is to move the size indicator back to where it was before we made a search. Now these elements are part of the set again, and this part isn't. So in order to keep track of state when we backtrack, we don't only need to keep copies of where this state pointer is. How big is this set? That is the only thing we need to copy between each time we make a search decision. Yeah. So something more I want to say. It's kind of space inefficient. You have to keep track of 2 arrays here, but on the other hand, it's very fast to backtrack, which makes it very suitable for specifically constraint programming. And I'll show some stuff later also where we can reuse this set, not only for domains, we can also use it for some constraints. How much time do I have? I think I have about 20 minutes left. 30?
Yeah, around 20 minutes should be good. Yeah.
Great. So we can also use this sparse set here with some other constraints. So I'll show you how to implement another constraint that's called maximum, where we have an array of variables called x's and y, another variable. The constraint says that y has to be equal to the maximum value of this array x's. So it's kind of like taking y is equal to max of x's. So we want to do what we want to do then is we want to do some pruning of all these variables. We want to remove the illegal ones, and like immediately we can see here that this variable, this x2 here, is kind of big. It's larger. It's well, I haven't explained that, haven't I? So what I mean with these columns here is that this part here, the lowest part, is the lowest possible value for x0, and this part here is signifies the largest possible value, and there's kind of some stuff in between here. So, for example, x3's largest possible value is smaller than y's smallest possible value. It's kind of nice to have this geometrical intuition here. And as you can see, x2, its absolutely largest possible value, is larger than y's largest possible value. And we want this to be equal to the largest one of these ones, which means this part here, let's see, I have a nice, hello. All the values that are bigger than y's biggest value, they can all be removed because they can't possibly be correct. Because hello. So these values can't be they can't be legal because y has to be the largest of these, and this is larger than that, so you have to remove that. And the same can be said for the largest possible smallest value, which means like if we're looking at these parts, the bottom of these rectangles, the largest, the ones that's highest up is this part here. So this is the smallest possible value that y can have, right? Because y has to be equal to the largest possible values of these variables, and this thing here is the largest of the smallest values. It's kind of confusing, but what that means is that all the values that are smaller than this one can also be removed. I want to disable that. So these values here are smaller than the smallest possible largest value. So what we need to keep track of when we're implementing this constraint is which of these variables have the largest value, the largest maximum, and the largest minimum. These are kind of the key variables that are relevant to this constraint. And the interesting part here is that this third variable, it will never be relevant to this constraint because its maximum is smaller than y's minimum. So this can't ever y can't ever be equal to x3. So we can just remove that, and we can just remove that for this part of the search tree. But for example, if we need to backtrack, it could be the case that x3 were pruned somewhere above us in the search tree, so it would maybe get bigger when we're backtracking. So what we want is a set that keeps track of which of these x's are relevant during this part of the search tree. So we want to remove some values when they are getting too small. We want to remove some variables when they're getting too small. And we can keep track of that using our sparse set from before. So instead of values in a domain, we store which variables are still relevant in this part of the search. And then when we backtrack, we can just use the sparse set's features to just put variables back again. Yeah. Did that make sense? It's kind of a confusing thing here. I'll take that as a yes. And lastly, I wanted to show how you can use this stuff for yourself. So you have this XKCD comic prepared where Qbal is being kind of an asshole and asks the waiter to solve an NP problem for him by specifying that he wants exactly 1505 worth of like appetizers, which is an NP hard problem. But we can solve this kind of easily because this is, despite like having being an NP problem, the problem set is quite small. So we can model this using a constraint solver. So what we have here is a language called Minisync, which is sort of a constraint programming language. It's kind of general, so you can use many different kinds of solvers, but one of them is a constraint solver. So what we do first is we define our input parameters. So target price is what the price that we want. It would be 1505 here. And then we have a menu size, which is how many of these menu appetizers there are. And then we have an array of prices. These are kind of normal constant variables, if you like, normal programming variables. They have only one value each. They don't have any domain. But this part over here, this is a var int, which means it's a variable that has a domain. We don't know its value yet. And what this kind of signifies is how many of each appetizers are in the order that we will produce. So it could be, for example, say if we have a value that is something like this, we say that we want 1 of the first appetizer, 2 of the second appetizer, and 2 of the third appetizer. Of course, we can't have a negative amount of appetizers, so I have to put a constraint that says that all quantities in this array have to be above 0, or above or equal to 0. And then here we have the kind of the meat of the problem. It is a sum constraint that says it takes an array and says that the target price here has to be equal to the sum. The sum is this kind of a fancy list comprehension syntax. So what we say here is that for all items in this range, 1 up to menu size, the quantity times quantity of an item times the price of an item means how much money do we spend on this particular item. And then when we sum that, we get what is the total price of our order. We specify that has to be the same as the target price. So this constraint is kind of all it takes to say that we want to solve this problem. And we can solve this in 2 ways. We can solve this for satisfaction, which means that when we solve this, we just want the first value that the solver gets. Whatever, we don't care about the quality of the solution as long as it satisfies our constraints. And something went wrong. What is this? This worked before. We did normal tunneling later, I guess. What's this? What? Oh, messed up. Why doesn't anything work in this tunnel in beta? Hello? I guess we'll do this. And as you can see here, we have a solution. We take 7 of the first appetizers, which would be, if you take up a calculator, 7 times 2.5, 15. And we multiply those together, we get 1505. This solution is kind of boring, right? It's just 7 of the same stuff. It's kind of a boring solution. We want some more variety of that. So what we could do is we could optimize this for something. We could say, for example, that we want to minimize the amount of appetizers that we, or maximize the amount of appetizers that we use, different kinds of appetizers. One way you can say that is we say that quantity, like in the quantity array, we want to minimize the amount of zeros that exists. So we want to remove as many of these zeros as possible. So we can then solve this to optimize the solution. So it won't take the first possible solution. We'll try to find the best solution. And when we do that, we get another solution here that kind of more interesting. It's kind of, we don't really want 7 of the same appetizer. Yeah, and Minisync is kind of an awesome thing. We have they have a website over here. They don't pay me to say this, but it's very nice, a very nice tool that you can use to solve a bunch of very hard problems. And you can use all different kinds of solvers, not just constraint programming solvers. So you can use, some may be familiar with mixed integer programming, for example. That is also some solvers also support Minisync from that. So you can use this high-level language to interface with kind of low-level solvers. And lastly, I just want to plug another thing, which is MiniCP. This is kind of where I learned all of this stuff. This is a free-to-use course that teaches you how to implement the constraint solver. You'll implement a bunch of things like search algorithms and a bunch of constraint propagators. They have slides on iCloud for some reason, and they have also video lectures on YouTube. So very nice course, highly recommend. And I'm kind of done, I think. Now I've moved quickly, so I really want some questions here.
Oh, did I interrupt someone?
Me. I thought I wanted questions.
Okay. Well, I do have one. I saw now from my very not in detail look at logic programming, I see a lot of overlap.
Yeah, exactly. So logic, I mean, so I think that there is a class of NP problems that are called SAT, satisfaction problems, that are basically logic. Some SAT solvers are also prologs, I think. So SAT is, you have a bunch of Boolean variables that are on the form of like, so disjunction, for example, B equals, I think, yeah. So yeah, you have just a bunch of, see something. So there are solvers that can solve problems on this form. We have like a basic, what's it called, predicate logic. And what you want to do is you get a formula, and you want to see if it's satisfiable or not, if you can make it true or not. So a SAT solver will find values for A, B, C, and D that will satisfy, that will make the formula true. And a bunch of those are also prologs, I think. So it's kind of similar, but they're more for solving these algorithmic problems. Like, I don't think you can't really program stuff with Minisync. I think you can do that with logic programming.
Yeah. Okay. Thank you. Other questions?
Yeah, not so much a question, but rather a few comments. So first of all, I found it really interesting. I only knew this kind of stuff from a very different perspective, which is like optimization problems in engineering, which essentially you do similar stuff, but you really need to focus down and kind of...
Was I on time, by the way?
Sorry? That noise, it's the dog. Yeah, so... sorry. So anyway, I found this really interesting, and I'm actually looking forward to try and apply this to other areas of what we're doing. So yeah, thanks for the thoughts about this in terms of a standard search. So it was yeah, very useful. So awesome talk.
Is somebody talking? No. No. I guess you could talk about another thing while I'm at it. So constraint programming is kind of very it's made for satisfaction problems. So they don't really work well with optimization problems. And that's kind of in the nature of how it works. It just removes the illegal values, and it never really tries to make it optimal. How a constraint solver works normally when it wants to optimize is it first finds any kind of solution, call it like X, for example, and then when it finds that solution, it wants to it posts a new constraint. So we have this solution that satisfies our problems, but we don't know if it's the best one. So for any, what it does then is it posts a new constraint that says that any new solution Y has to be larger than X, which will trigger some new pruning, will remove some values maybe, and then you'll keep on searching the search tree for solutions that are bigger than X. And then when you continue doing this process until you find some solution that until you have exhausted the entire search tree. But so this works kind of well for stuff where I can reasonably search the entire search tree, but that isn't always the case, especially for larger problems. You will basically never complete this entire search tree. So what you can do then is you can give up the constraint that it has to be the absolutely best value, but just as good as a value as you can find. So what you can do then is a technique called large neighborhood search. So it will still continue to do find some form of solution somewhere, a feasible solution like before, and then when it has done that, it has a bunch of variables that are fixed to some value, right? So it takes a random selection of those, say Y in this example, and just unfixes that. It makes it have its entire domain again. These ones are still fixed to some value that has been part of the solution, but we reset Y and restart the search process and try to find a solution that is better than the one we have found so far. And we can continue doing this. So we just continue. We try some subset of fixed values, variables that are fixed to some values that we think are good, and then the other part we discard and we restart the search process, kind of halfway through. And what this does is, when in the search tree, you can kind of, instead of going back all the way up, you can just kind of, once you've found one place, you kind of start somewhere in the middle and continue searching. So what you can do then is you can kind of skip searching in the top part, which is kind of unnecessary, and you can probe different regions in the bottom of the search tree. So it's kind of a new technique, I think, which makes optimization problems a lot faster for constraint programming, and kind of makes it so that constraint programming is a valuable competitor in the space of solvers. This is kind of a cool thing also, because it kind of combines the technique of another technique called stochastic local search that kind of works in the same way, that it's you have some random selection of values, and then you kind of just probe the neighborhood. You just try changing some values and see which change is making the biggest change, positive change to our optimization value. And in that way, it kind of searches through the search space, sort of like gradient descent, I guess, but in a more discrete manner. So it kind of combines the power of stochastic local search with the power of constraint programming to make superpower. Now I'm done for real, I think.
Thanks. Can you hear me now better, by the way? Lejon, can you hear me at all? I guess not.
Thanks.
Yes.
No more questions?
I don't think so. I'm not sure if QYU has a follow-up, but...
And I guess that was it for me. Thank you very much.
Okay, thank you. Yes. Thank you to Lejon for that excellent presentation. I think I've pronounced your name 3 different times now, but that's besides the point. Now, for our final talk today, we have Comuser Frud giving us a talk about how he uses Emacs as a non-programmer. Yes, the floor is yours. Cool.
One moment while I export my presentation one more time. Let's see. All right, so. One moment, I'm just getting my screens set up the way that I want them to be.
In the meantime, I can answer a question from chat. How do you pronounce my name? It's at least in Swedish, you say Lejon. No, you know.
This is great, thank you. In my mind, up to now, you've been Lejon.
Somebody posted a question in the chat. I don't quite understand. What do you mean? I think it's Q.
All right, well now I'm not able to share my screen, so let's see, 1 second. All right, well, I'm going to try and leave and rejoin and then see if my screen sharing will cooperate. I'll be back in just a second. Okay. All right. So, are you able to see Illiterate Emacs?
Yes, we can.
Wonderful. Okay. Well, hello. Thank you for joining me. So this is Illiterate Emacs, the Eternal Yak Shave. A little bit about me. So I'm not a programmer by trade, and that's kind of the perspective that I'm trying to provide today. Is what does someone who is not a software engineer, what do they use Emacs for? And yeah, so hello. My name's Kevin. I live in the Pacific Northwest of uh, United States, and I'm actually a CAD drafter by trade. And I work for local government. I've always thought computers were neat, and very much enjoy using Doom Emacs. So yeah, kind of what I'm going to be talking about is again this sort of non-programmer's perspective of Doom Emacs and how I approach it and what I use it for. I and kind of maybe I was kind of envisioning providing maybe some insight to people who don't necessarily like I want people who are I would say maybe power users or who are software engineers to have some more insight into someone who does not come from that background, just to help people understand uh, where people are coming from. Like to I know that some of the same issues are brought up over and over again for people struggling with using Emacs, and it might be hard to anticipate what the issues might be when you are very well versed in Emacs and in eLisp. And then just for me, rather than seeing Emacs and Doom as a tool to um, complete, as a tool to complete my work, I see it as more of a playground and an end in itself. Another thing I want to talk about is maybe a interesting perspective. So I have configured and installed Doom Emacs on so many different systems that I think it would be interesting to mention. Just as kind of a brief list, I've put it on, Windows 10 using Windows Subsystem for Linux 1 and 2. I've Windows 10 Enterprise, and then like Windows 11 with its WSLG, which allows for Linux native GUI, and then I have it on Ubuntu and on a desktop and on a VPS, and I've had it on Manjaro and Arch, uh, and Termux on an Android, and then there's even at one point in time. So now Windows 11, you can have the Windows subsystem for Android, which allows for Android emulation. So I put on Windows 11 on the Android emulator using Termux, installed Doom Emacs on that. That was interesting. And then I just want to also talk about how anyone can use Emacs and Doom Emacs. It is, I know, it's there's the sort of infamous learning curve, but I'm the type of software user who sort of doesn't take the time to understand what they're doing before they start doing it. And even though I've been using Doom for at least a couple years now, my depth of understanding when it comes to eLisp in particular, like I half the time don't know what I'm doing, but I'm able to sort of bumble my way through to a usable environment. So when did I start using Emacs? I think I mentioned it probably it's hard to say, but like 2 or 3 years ago. Um, so yeah, I knew that Emacs existed. I'd heard about it. I'd used Linux before, like the first time, maybe like 10 years ago. But yeah, I've really liked it, but I never really used Linux as my daily driver until about last year. And I'd always kind of used uh, Nano or on Windows Notepad++, but I fell down a rabbit hole when I saw someone using a terminal that had the terminal prompt was using power line separators, and I was like, wow, that looks really cool. Somehow, eventually, that led me to Spacemacs, and so I first started using Spacemacs, and to me, it was just sort of a novelty. It was interesting, but I never really, kind of gave it up after a couple months, and then I stumbled over a series of YouTube videos about Doom Emacs. Uh, I think the channel is it's Zeist Programming, and he has this Doomcast series. And I think there are about 27 videos to date, and those were an excellent gateway to learning more about Emacs in general and Doomacs specifically. Uh, and once I kind of saw that, I became obsessed and started to use Doom in earnest. And again, just because I saw it as this interesting thing, it looked interesting. I'm very much, uh, I, I chase after novel, new, and shiny things, and it looked interesting. And so, without really understanding what I was doing, I began copying, huge swaths of other people's configurations and throwing it into mine and breaking things. And yeah, over time have gotten better, but that's kind of the where I'm coming from as a user of Emacs is someone who just thought it was interesting, dove headlong into it, and still has a shallow understanding of eLisp, but is able to uh, set up a usable and comfortable environment for myself. But so, what do I actually use it for? Uh, well, I would say my main use is, mainly using org mode for notes, for taking notes. So I have been working remotely uh, for 2 years now, since sort of I was temporarily sent home to work remotely towards the beginning of the pandemic, and that eventually transformed into permanent remote work, working from home. And I don't operate well in terms of like phone calls and sort of Zoom or Microsoft Teams meetings, paying attention and absorbing information. So I take advantage of org mode for just taking copious amounts of notes. And org mode, also the way that it's structured, at least the way I structure it, as far as outlining and taking notes that way, really works well for my brain. And so I will take notes for every project, every phone call, every meeting, and really rely on that for work. And then also, excuse me, I play Dungeons and Dragons, and I take notes to keep track of campaigns as a player and as a DM. And then I use Org Roam, but really not very much. I could do it with other packages, but because I just use it for daily journaling at this point. I've just sort of dipped my toes into it, but that's something that I use on a daily basis. And so yeah, I also use Doom and Emacs for task management. Certainly not to the extent that other people do. It's pretty basic. Again, it's relying on org mode, and I don't really use agenda, but it's basically I have like a single org file that I use to track my professional projects. Each project, kind of has a headline broken down into tracking, action items and basic information, and then I'll have like a link to an external another org document that's just notes for that project. And so I'll have like bullet lists of like to do items at its most basic. And I kind of do something similar for I do something similar for my personal projects as well. It kind of just have like a single uh, org document that I believe at the moment I call manage self, that I use to keep track of my personal projects. So beyond org mode and Emacs, uh, I, I guess I would call it system configuration management. I didn't want to just say like dot file management, but that is certainly a large part of it. And Maggot is something that I knew about but didn't start using until last year. But now I can't imagine not using it uh, uh, for my version control. And so yeah, I use that and Emacs to uh, manage all of my system configurations. I like, you know, uh, setting up my environment using, you know, config files rather than GUIs. And I like trying different distros and things. So I'm often starting from scratch, although recently I have gotten better about, having a sort of basic repo that I use for setting up a system. And then, just as a basic text editor uh, for everything. Emacs is an excellent text editor. It especially with evil added to it. So I do some programming, but it's just sort of one small piece of what I use Emacs for. Like I do some Bash scripting and Python scripting. I wouldn't call it Python programming. And I've done a little, used a little JavaScript to create some Discord bots. Uh, so like that's pretty much the extent of what I do as far as programming and Emacs. I also do. So I don't know if you're familiar. There's as a CAD drafter, I use AutoCAD, and they have their own Lisp called AutoLisp, which is actually my first Lisp language. Was this weird CAD Lisp called AutoLisp? So I use that a lot and write a lot of those little AutoLisp scripts and things. And I think it's because I had an early exposure to that I felt somewhat comfortable looking at eLisp and Emacs. Uh, and I also use Emacs I've tried, for as a feed reader using lfeed, and I've set up, email, and I use Gmail primarily, although I did just set up a Fastmail account, which I'm planning on switching over to. But that, and then like doing some blogging, those are things that I've, amongst many other just random little one-offs, I've tried out in Emacs that haven't made it, their way into my routine or my workflow. Um, and then, I haven't done much literate programming, but I do enjoy using a literate config for Doom. I haven't used it for any other like system dot files, but with Doom, I like using that. And then, kind of, eh, one point I want to get across is that I use Emacs to use the Emacs. For me, yak shaving is the means and end. So one of my main hobbies is using Doom Emacs and configuring it just because it's interesting, and so I don't rely on it. I mean, I do more so now as far as like taking notes and managing my system and task management and things like that. But for a long time, I saw Doom Emacs as not as a tool, but as a toy. Any practical use that I squeezed out of it was a bonus. Uh, so I could just try all kinds of stuff. And I wanted to learn more about eLisp so that I could, you know, do more interesting things with Doom and with Emacs, but not to accomplish something. The accomplishment was doing something with Emacs for fun. And I see it less of a toy now and more of a tool, but still, that is kind of the my perspective of Emacs and Doom is this playground, really. Uh, yeah. So I also did want to touch on the many different ways or places like that I use Emacs. So I had mentioned that Windows Subsystem for Linux. There's the first version of it and there's the second version of it, which have their differences. And using Windows 10, I, my work desktop is Windows 10 Enterprise, but it's on the government update ring, so it's even slower updates. And for a long time, I used Windows Subsystem for Linux 1, and then used an X server within Windows 10. And probably the craziest thing I did, and I did this for a long time, was I had my personal desktop with Windows 10 that I would use to remote into my workstation PC that also was Windows 10. So it was RDP from my personal computer to my professional computer. And then from there, I would use Windows Subsystem for Linux to remote into a VPS that had Ubuntu on it. And that was where I had my Doom Emacs configuration. And I would use X forwarding to display it. So it was like this weird convoluted chain to get to Emacs. And so using it that way for a long time, because of a weird setup, now using it natively is wonderful. And yes, I've also used Windows 10 and 11, and 11 now has this sort of, rather than an X server, has uh, it allows you to display Linux GUIs natively under the hood. It's a mix of whatever Windows Subsystem for Linux 2 is. It's a different Linux VM that's using Wayland and an RDP protocol. But yeah, So yeah, I have also used Ubuntu and still have that VPS with Ubuntu on it that has my sort of original Doom Emacs configuration, and then have dual booted my computer with a desktop version of Ubuntu and used that for a long time with Doom Emacs. And then sort of my first Linux daily driver was Manjaro. And used Sway Window Manager and Wayland, and I really lived in Emacs with that, and that's sort of where I became more dependent on it and had my first literate config, and then I last year got a little ThinkPad that I put Arch on, and use that every single day, and have used Emacs to help manage and configure that laptop from the moment I got it. And Emacs is always open. Yeah, so that's about it. And I, I mean, if you want to see what my configuration, my Doom Emacs config, I have a literate config. I have a couple actually. If you want to kind of understand what the configuration of someone who approaches Doom as a non-programmer, and also I am not systematic. I am not organized. It is it it might give you some insight into people who are coming onto Discord and going to the help channel and asking questions, and then you're answering those questions, the same questions every day. But yeah, thank you for listening to my yeah, that's about it.
I thank you. That was an excellent talk. It was very interesting to see the different ways that Emacs is not only used, but to see it from a perspective that we don't usually see. I remember we were discussing this, I think, when you brought up your talk, that there are so many different ways people use Emacs. I think there was a pastor who used Org Rome to plan out sermons somewhere. But our community is so geared towards programming, it can sort of be both blinding. So it was a very good talk. Are there any questions?
Yes. How high was the latency on that cursed chain of remote connections?
It wasn't too bad because, so interestingly, I had my personal computer in my basement, and then my workstation computer was upstairs, and I would remote into that. So it was on the same network, and then my VPS was actually at a data center that coincidentally was half a mile down the street from me. And then not only that, sometimes my work computer, I would be required to connect to their VPN to access what used to be on-premises network drives, but those network drives were moved to a data center, which happened to be the data center down the street from me. So kind of everything I was connecting to was very close by geographically, oddly enough. Latency was not great, but it was okay.
Nice, I guess.
Unless there are any more questions, then that brings us to an end. I would like to thank everybody who presented, and some of the people who ended up didn't, because we actually finished 20 minutes early from my proposed schedule. So I'll call that good planning, or whatever you will. And yes, just thank you to everybody who came. And yeah, I shouldn't talk too much because, yeah, let's keep it short and sweet. Okay.